My name is Kumar. So the topic of my research is effect of elevated temperature on the physio-biochemical responses of Kappaphycus alvarezii. So moving on into the introduction, the eukymatoids, which are generally known as red seaweeds, include from the genera Kappaphycus and Eucheuma, which are cultivated in the regions with a tropical or subtropical climates. So for instance, Kappaphycus alvarezii are mainly cultivated in the Coral Triangle, with the Philippines, Indonesia and Malaysia ranked among the largest producers. So the main reason Kappaphycus alvarezii is being cultivated in large scale is due to its substance called kerogen. So this kerogen has a great economic value. So moving on into the substance kerogen. So kerogen is a family of gel-forming and viscosifying polysaccharides and also a widely demanded hydrocolloid. So kerogen exists in three different types, which is the iota kerogen, kappa kerogen, and lambda kerogen. So among these three kerogenins, kappa kerogen is highly favored in the industry due to its ability to form strong gels. So kerogen is either extracted into semi-refined or refined kerogen prior to processing or manufacturing. So kerogen has a variety of applications, which includes as emulsifying, thickening, and stabilizing agent, also widely used in the pharmaceutical and cosmetic industry, and used to improve the quality of meat products. So examples of products which has kerogen in it includes cheese, ice cream, yogurt, butter, and etc. So, due to this increasing demand of kerogen, farming of Kappaphycus was set up. So on the left is a Kappaphycus alvarezii cultivation farm in Sempurna, Sabah. So the main reason farming of Kappaphycus was set up or established is as source of income and for commercial production. And secondly, offering a means of livelihood to the local community or the coastal communities. And lastly, to meet the increasing industrial demand for kerogen. As the demand for kerogen increased and more farms were set up, there were few challenges faced by the farmers or cultivators, which include seaweed price fluctuation, ineffective farming technology, and also occurrence of ice disease. So ice disease occurs when there's an increase in seawater temperature, which inflicts stress on the seaweeds to cause whitening of the tissue. So here on the left you can see the circled part is the ice disease, where the whitening of tissue occurs. So ice disease leads to a significant decrease in seaweed production, decrease in kerogen yield. It also reduces the quality of the kerogen, such as the viscosity and gel strength. So my research objectives includes to investigate the physiological response, which includes the growth, photosynthetic performance, and biochemical response, which includes the pigment contents, phycocolloid quality, and reactive oxygen assay of Kappaphycus alvarezii at elevated temperature, and to identify the range of temperature that can be tolerated by Kappaphycus alvarezii from Malaysia. So moving on into the methodology, sample collection was done in Sempurna, Sabah, and the seaweeds were brought back to the laboratory for stock maintenance and acclimatization under the standardized temperature, irradiance, salinity, dark light regime, and continuous aeration. So some of the samples will undergo morphological and molecular identification. This is to ensure the samples brought back from Sabah were Kappaphycus alvarezii. So the temperature tested was 28, 32, 36 and 40 degrees, and 5 replicates was done for each temperature. To start on was the growth response, which was done using the fresh weight measurements every 2 days, followed by photosynthetic response, which was done by using a chlorophyll fluorescence monitoring by PAM fluorometer, which was also done every 2 days. And moving on into the pigment contents, the pigment we looked into was chlorophyll A, carotenoid and phycobiliproteins, which includes allophycocyanin, phycocyanin, and phycoerythrin. This was done on day 0 and final day. There is variation on the final day because seaweeds incubated at 36 and 40 degrees could not withstand up to day 14. Therefore, we had to stop 36 degrees at day 10, 40 degrees at day 2. Moving on to kerogen quality tests, which includes kerogen yield, gel viscosity, and gel strength, which was also done on day 0 and final day. And lastly is the reactive oxygen assay, which was done using the DCFH-DA fluorescent dye. So these dye attracts the ROS produced by the seaweeds and transform them into the DCF, which is a fluorescent substance. So these can be measured using a spectrophlorometer. So this was done on an hourly basis to look at the response of stress using the ROS production. And lastly is the statistical analysis were computed using Statistica software. Moving on into the temperature treatment. So moving on to the growth response, as you can see on the graph on the left, the Kappaphycus alvarezii grown at 28 degrees Celsius displayed a higher specific growth rate compared to the rest of the temperatures, and growth rate was maximum on the second day for 28, 32, 36, and higher specific growth rate was recorded at 0.5822, which is at 28 degrees Celsius. So from day 2 onwards, the specific growth rate decreased distinctively with increasing temperatures above the optimum. So Kappaphycus alvarezii grown at 40 degrees could not survive. Moving on. As you can see from these two pictures, which is the before treatment and after treatment, there are changes in the conditions of the seaweeds. As for seaweeds incubated at 40 degrees, it was completely bleached by end of the treatment. For 36, it was mildly bleached, and as for 28 and 32 degrees, the seaweeds were not bleached. Moving on into the photosynthetic response, the photosynthetic parameters that we looked into includes maximum quantum yield, maximum relative electron transport rate, and light harvesting efficiency. So high temperature stress reduced the photosynthetic parameters, indicates that the structural and functional disorder of the photosynthetic apparatus and damage to PS2 had occurred. So according to the graph on the left, the maximum quantum yield of Kappaphycus alvarezii incubated at 28 and 32 fluctuated around 0.5 to 0.6. So this shows natural variability of FVFM and showing an active photosynthetic rate. While at 36 degrees, the FVFM declined noticeably to 0.438 after 8 days of incubation, and further increase of temperature of 40 degrees distinctly lowered the FVFM value. Moving on to the rATR max and alpha, the rATR max value of Kappaphycus alvarezii incubated at 28 and 32 degrees remained in the range 170 to 190 throughout the 2 weeks of incubation, whereas the photosynthetic efficiency of Kappaphycus alvarezii incubated at 28 degrees fluctuated between 0.16 to 0.18, and highest value was recorded at day 4. So incubation at 36 degrees noticeably inhibited rATR max and alpha value, whereas the degree of inhibition increased with incubation time. And as predicted, Kappaphycus alvarezii at 40 degrees had a sharp decline of rATR max and alpha, which indicates the seaweeds could not survive. So moving on into the pigment contents, as you can see from these two charts, incubation of Kappaphycus alvarezii beyond the ambient temperature, which includes 32, 36 and 40 degrees, displayed a reduction in pigment content. So the magnitude of inhibition was positively correlated with the increase in temperature, which means higher the temperature, the higher the magnitude of inhibition. So significant differences were observed between the 4 temperatures studied. Phycobiliproteins, chlorophyll and carotenoid content of specimens incubated at 40 degrees was significantly inhibited compared to the other temperatures. Moving on into the kerogen quality, as you can see from this chart, the kerogen yield and quality decreased with increasing temperature. So significant differences were observed between all 4 temperatures for kerogen yield, gel strength and gel viscosity. So gel viscosity of Kappaphycus alvarezii at 36 and 40 degrees showed no significant differences, but significant differences were observed for specimens at 36 and 40 degrees for kerogen yield and gel strength. As you can see from these pictures of the gels, difference in gel color also indicates the reduction of pigment content. So moving on to the reactive oxygen assay, as you can see from this table, the incubation of the strains at different temperatures induced the production of DCF fluorescence. So we looked into the absolute DCF fluorescence. So highest ROS production was produced in first hour and reduced thereafter. with significant differences noted for specimens incubated at 36 and 40 degrees. So highest ROS production was by specimens incubated at 40 degrees and on the first hour. To conclude, Kappaphycus alvarezii was able to grow in wide range of temperature, but stress was observed at above 32, 36 and 40 degrees. The temperature between 36 and 40 degrees can be considered as upper limit temperature for the studied strains. So the growth rates, photosynthetic performance, fiber quality and pigment contents were reduced as temperature increased, while the production of reactive oxygen species increased with temperature. So we believe this study provides a basis for future work on long-term acclimation to elevated temperature and multivariate mesosome studies to identify heat-tolerant strains for sustainable cultivation. So these are the references. I would like to thank the research grant, Global Seaweed Star, Institute of Ocean and Earth Science, and Institute of Advanced Studies, University of Malaya. So thank you.